part 2. So here we shift gears. So the first lecture was about constraints. I think it was fairly uncontroversial. It's really the data. By the way, one thing was not clearly realized during the coffee break. So when I was saying all this material comes from a hot disk, condensed, was reprocessed, and this, because we want to be factual, this concerns everything we find in meteorites, so in asteroids, okay? Comets are another thing, and we don't know, because we don't have a piece of comets in our hand. So if you want to remain factual, the fact that material come from a hot disk and condensed was processed in the disk and so on, this concerns whatever we find in meteorites, and comets, we don't know. In the second part, we try to make sense of all these constraints and talk about all the phases of formation of a planetary system like ours that can explain what we see. Of course, models are models, right? They're never perfect. There can be different models. Models can be believed one day and not believed the other day. So keep this in mind. Also, because models are produced by people, there is some affection towards models involved. So there are also biases, So I will tell my story. It's obviously a little bit biased as always. We try to be, as I think, open as possible, but keep this in mind. I cannot speak about everything because it take the entire week. So I have to make my selection of what I think are the models which are the most credible, but you could find other people thinking differently. I will try to mention when there are controversies. So let's having said that, let's start. So how do we think planetary systems form? The very observations that the solar system is coplanar prompted Kant and Laplace to say that planetary system form in a disk surrounding the forming star. And today we observed young stars, they are all surrounded by disks. There is no doubt that planet formation happens in a disk. It's not a model now, it's observed. So what happens in a disk? First, the disk is composed of gas and material, dust, maybe dust that pre-exists or maybe dust that condenses out if the gas was initially too hot for dust to exist. And once dust starts to form, so little solids start to form, the dust dynamics is characterized by two basic phenomena. The first is sedimentation. So the dust that is initially uniformly dispersed in the disk tends to settle on the midplane of the disk. And the settling time scale is faster for bigger grains and slower for smaller grains. There is some turbulence in the disk always, even if probably very weak, but non-negligible. So the dust never settles into something indefinitely thin, but creates clearly a dust disk that is much narrower in scale height than the gas disk, and this is observed. The other process, dynamical process for the dust, is the drift towards the central star. This is due to gas drag. The gas orbits the star as the dust, but the gas feels the gravity from the star, but also its own pressure. And the force coming from the pressure of the gas is directed outwards. So the net force that gas feels is gravity of the sun minus the pressure force. So it's a little bit weaker than the gravity that the dust feels, which is only the gravity from the sun. So to be in orbit, on a circular orbit, the gas has to orbit a little bit more slowly than a dust grain. That means that as the dust orbits the sun, it feels a headwind from the gas that slows down the grain, makes the grain lose energy and angular momentum. And this is why the grains tend to drift towards the star unless the pressure gradient is reversed somewhere. But in general, in a power law disk, density disk, this is not the case. The dust, in addition to settling and moving towards the star, also tends to coagulate. This was to say that the drift rate, towards the star is a function of the size of the grains as well. And whereas settling is faster for bigger grains, where the radial motion is maximum for some intermediate size. So it's small for very small dust, because the very small dust is coupled with the gas, and it's small for planetesimal, because planetesimal are massive. It's difficult to slow them down by gas drag. And so the drift rate is maximum for some intermediate size. And what is the intermediate size? Depends on where you are, how much gas you have. So for instance, in this case, it's about a meter. So, but it can change from one place to another in the disk. So the dust tends to coagulate. So at the beginning, you have, when the dust starts to condense, it's monometric in size, nanometric in size, and then these monomers tend to stick to each other, of course, through electrostatic forces. There is no gravity at this level. And this forms fractal structures. And these fractal structures can then collide with each other and stick to each other and merge. And merging typically makes a bigger grain that is a bit less fractal than the initial grain. So this is a process of compactification. So you get the stuff which is less and less fractal, more and more compact. And you can also have thermal event that sinter these grains by melting them in part and then recrystallizing in part. This is probably what happens for chondrules, and then you form a hard sphere like a chondrule. But when grains collide, keep growing, and then they collide, of course, because they have more mass, they have more energy. And when the energy is large enough, when you have a collision between grains, you start to lose pieces. And when the collision brings too much energy, the grains can destroy and restitute the monomers into the disk. So there is a full literature doing experiments of how grains stick and up to which size. Germany is particularly known for this series of experiments. They've also been done in absence of gravity in Trop Towers, in the International Space Station, in centrifuge. And the result is that it's difficult to grow big stuff. If your monomers are made of silicates, typically maximum you can build is something of the order of a millimeter. Maybe if you have water ice is more sticky. That's why you play snowballs when it snows and not sandballs on the beach. And so you can maybe form something bigger of the order of centimeters. Some people say up to a decimeter. Anyway, it's stuff small like that. And so not a planetesimal several kilometers, even less a planet. So you may wonder whether this is a limitation. Somehow the experiments and nature is better than we are able to do. But again, when we take a meteorite that didn't melt, so a chondrite, and you look at what is the meteorite is made of, all these chondrules and CIs and so on, and you make a statistics of their size, most of these things are sub-millimeter in size. It's very rare to find something bigger. Some CI can be up to a centimeter in size, but most of the components are millimeter or less. So it's probably true that this process of coagulation brings material up to millimeter in size, and then this is what nature uses to make planetesimals. And of course, and these grains don't stick anymore. So how can you make a planetesimals with millimeter size spheres and not sticking to each other? This has been a huge problem in the community for decades. And we are lucky now that at least we have some ideas that have been developed in the community that give some hint of what should happen. The idea is that when you have the disk of gas with these millimeter size grains, so this is a complicated fluid dynamics, and there are several processes, a number of processes that can change the distribution of the dust with respect to the gas and create clumps of dust. There are several processes. Two are mostly studied, but there are others. One is called the Kelvin-Helmholtz instability. This is an instability related to the settling of grains on the midplane. The other one is the streaming instability, and this is the instability that comes by the radial drift of grains towards the sun. So I will give you two examples, right, in animation. So this one is about the Kelvin-Helmholtz instability. So what are we seeing here? We are seeing the dust distribution over time. The axes are the vertical direction, 0 is the midplane, and this other arrow is the azimuthal direction. So we are at a given distance from the sun, and the azimuthal direction is the circle around the sun. And so the color shows the dust to gas ratio. Initially, the dust is a little bit concentrated at the midplane. With time going on, we will see that this layer tends to become narrower and denser in dust, so the color will change. But this triggers some turbulence, and then you will see that the band will not be a band anymore. So let's go. Time starts, you see this band becomes narrower and denser, the red colors, and here turbulence kicks in, and this creates vortices and turbulent structures, and the dust tends to concentrate in these structures. So you don't have a uniform band of dust anymore, but you have dust concentration in clumps. This is during sedimentation. During radial drift, it's about the same. Now I don't have a movie here. I have 3 snapshots. They show, now we see the dust distribution on the midplane. Okay. So this is the x-axis is the radial direction, the sun being to the left. And this one is the azimuthal direction. And it's a plot on the plane, on the midplane. The colors show the dust density with respect to the initial one. So at the beginning, it's totally uniform. After a little bit, you have that the dust is not completely uniform anymore. You see some filaments starting to form. A little bit later, these filaments break down in clumps, and then these clumps become denser and denser. Okay, and so this is called the streaming instability. So, like before, the net result is that you start from a uniform distribution of dust, and you end up in forming clumps of dust. The idea is that when these clumps of dust are dense enough, the collective gravity of the dust in the clump keeps the clump together. And so the clump cannot be dispersed anymore, and the dust can only slowly sediment and collapse on a macroscopic object. And the simulations that follow also this phase show that typically the objects you form, it's about 100 kilometers in size. This is because clumps which are so big to form immediately, series-size objects exist, but are extremely rare. Clumps which are very small are much more frequent, but if the clump is small, the gravity is small, and then the perturbations in the disk destroy the clump. And so the most successful clumps are those that lead to 100-kilometer objects. So we go, according to our current understanding, directly from the size of grains that are millimeters in size to the size of an object which is 100 kilometers in size, without passing through the intermediate scales. So what we see today, like smaller asteroids or smaller comets, they should be fragments, collisional fragments of the original planetesimals. And what we see, bigger planetesimals like Pluto, Ceres, and so on, they should be planetesimals that have accreted other planetesimals that started to grow towards the status of planets. So again, this now, I think the community is pretty behind this. The debate is which hydrodynamical instability really produces the clumps, how much the turbulence that can be the disk and so on, becomes very technical. But everybody agrees that this is the only way forward to form planetesimals like asteroids or Kuiper belt objects. A proof that, sort of convincing argument at least, proof that this is indeed what happens comes from the fact that we observe in the Kuiper belt a lot of binary objects, and this process of collapse of the self-gravitating clump of dust tends to produce binary objects. And this is because when you have a clump of dust, that's what you see here, I will launch the animation in a second, this clump typically has some angular momentum. It comes from the streaming instability or the vertical shear instability or everything turns, right? So it has some angular momentum. And because it has some angular momentum, it cannot collapse in a single object because a single object has no angular momentum. So when you simulate the collapse, this is typically what you see. So the clouds start to collapse and tend to form a single object, but there is an excess of angular momentum. So there is not, everything does not go into a single object, and you form a binary, the two objects rotating around each other and some other objects that leave the clump. And it's interesting that in the Kuiper belt, we observe that the orientation of the plane of the binary, right? And so, for instance, the observations, which are this shaded curve, show that 80% of the binaries have a prograde orbit, and only 20% have a retrograde orbit. And in this work, Nesborn et al. Have taken the clumps coming from the streaming instability, so their distribution of angular momenta, and follow the collapse. And what they found is the continuous line, which fits what is observed very well within the error bars. And this is the only model known so far to reproduce the orientation of the planes of the binaries. And this is considered in the community as very strong indication that indeed planetesimals form by the collapse of particle clouds, sometimes called pebble clouds. Okay. All problem solved? Not really, because in order to trigger these instabilities, you typically need to have a dust-to-gas ratio, which is a few times the one that should characterize the initial disk, which is 1%. We know it's 1% from the solar metallicity. What this diagram shows is what is the dust-to-gas ratio that you need to have in your local portion of the disk in order to have clumping as a function of particle size, which is here represented by this parameter called the Stokes number. And it's something that's related to the friction of gas, but basically it's related to particle size from small to large. And then you see that, and typically you don't expect anything with Stokes number larger than 0.1. And then you see that the smaller are the particles, the higher has to be the dust-to-gas ratio, of order of 6%. But even if you go down here, which is sort of the biggest particles you can expect from coagulation, you still need 2% dust-to-gas ratio. You have only 1%. Factor of 2 away. And this is for a disk that has a very weak turbulence. Alpha is an indicator of the turbulence in the disk. It's difficult to imagine less. Also, observations tend to show that this a typical flow of turbulence in disks. So we have a problem there. Maybe something just quantitative issues that we don't understand very well. But if this is correct, there is a little gap between the amount of dust that we have at our disposal in the disk and that needed to start to form the planetesimals. So if this is true, in order to get forms planetesimals, somehow the dust needs to pile up in some locations of the disk so that the local dust-to-gas ratio increases from the average one in the disk to something a few times higher. How can that happen? So scientists have worked on that, and the idea is that this can happen near condensation lines. Condensation lines are the location in the disk where the temperature transits through the value that is associated to the condensation on a chemical species. The most prominent one is the water snow line. The disk is warmer inside, cooler outside. So inside you can have only water vapor. And then there is some location where the temperature in the disk is of the order 170 Kelvin. And there the water can condense. And then beyond you have ice grains and not water vapor. So the fact that you condense ice grains immediately changes the amount of solids you have, because you have also the ice that participates to the budget of solids and not only the refractory material. You also have the fact, as I showed before, that presumably once you start to have ice, you can grow bigger particles. And so the idea is that ice and refractory particles, ice being blue, refractory particles being red, accrete with each other to form bigger pebbles, which have maybe a refractory core with an icy mantle. We don't know very well. And this stuff migrates towards the star because, as I said at the beginning, because of gas drag, all particles tend to drift towards the star. And when they drift towards the star, they pass through the water snow line. They pass from the cold side to the warm side. What does it mean? That the ice evaporates and becomes a vapor. And so this releases a lot of water vapor and releases the silicate grains. Because the silicate grains are smaller, they drift less fast, so there is a sort of traffic jam. Because, when you are on a highway, the density of cars in the highway, when everybody can drive at 130, is less than when everybody is low to 50, because when they become compact. Because if you want to conserve the mass flux, then the density is inversely proportional to the speed. So you have a pile-up of refractory grains on the inside of the water snow line. The vapor that is released here, part of it can diffuse out because of diffusion, and as it diffuses out, it recondenses and recoating this particle of ice. And so at the end, this process creates a bump in the surface density of solid material. This is a way in which you can increase locally the dust-to-gas ratio and reach the threshold to produce planetesimals right away by clumping. So it's considered to be a sweet spot to form the first planetesimals. Now, we have seen in the previous lecture that we have early planetesimals, parent bodies of iron meteorites, in two isotopic classes. So if you have only the snow line doing this job, how can we have two different categories of planetesimals that form early? Probably the snow line is one spot, but we need another spot. This is something on which I worked on. I will show you what we obtained. Of course, it's our model, so there is some bias in it. And the idea we introduced based on some hydrodynamical simulation of star and disk formation is that most of the material that is accreted by the star falls close to the star. So the disk is fed predominantly close to the star. And as long as this is true, then the disk tends to spread viscously. And so the radial velocity of the gas is positive as long as you have accretion continuing on the disk in the inner part. The radial velocity of the gas is important because if you look at the radial velocity of particles, this is actually affected by two terms. One is the drag that I mentioned before, because the gas orbits in a sub-Keplerian velocity, the dust is slowed down, and so this gives a negative term. Okay. But the gas is also moving radially. UR is the radial velocity of the gas. And if the gas is moving towards the star, it also pushes the dust towards the star. But if the dust is moving outwards, it opposes the drag. And this has, at the beginning at least, when the radial expansion of the disk can be vigorous, this has an effect. So for instance, this diagram shows it's the distance from the star, the time with respect to time zero. And these three regions are the regions where the dust moves towards the star, away from the star or towards the star again. And of course here, because you have a region where the dust moves away from the star and here it moves towards the star, then of course you can have dust pile up. And the colors here show the dust to gas mid-plane density ratio. So you start to accumulate material in the inner part of the disk because of this effect. And if you take into account that also silicates can sublimate and condense, then you can get the same as I showed before for water, but for silicates. And so locally close to the silicate line, you can reach dust-to-gas ratio of order unity, which allow planetesimals to form. And this could be the second site where planetesimals can form very quickly on a time scale of a few 100,000 years, and so be the parent body of iron meteoroids. So some planetesimals should form very quickly at the snow line, others should form very quickly at the silicate line. It's two different locations, so we can have different isotopic properties. Indeed, this idea that the disk is fed close to the star and spreads outwards can explain the origin of the isotopic dichotomy. This is a subject of huge debate. What sets the isotopic dichotomy in first place? But I think the most convincing argument is based on the fact that we have the non-carbonaceous material that forms closer to the sun, the carbonaceous material that forms farther out, and it's the carbonaceous material that is the closest to the isotopic composition of CAIs. But CAIs formed in a very hot disk, so very close to the star. So the idea is the following, as described in this paper by Nan et al., is that when the star forms, the gas falls very close to the star due to angular momentum breaking, so removal of angular momentum. There are very nice simulations in the group at CA of Patrick and Bell showing that indeed the disk starts to form very, very small and spreads very quickly, about 1 astronomical unit per year. Okay, so you have this, the material falls here, has solar composition. The material starts to spread out, CAIs condense, and they are transported outwards with the gas. And so everywhere in the disk, you have material coming from this early gas of solar composition. The CAIs have the same isotopic composition of the sun, at least for what concerns oxygen. Then later on, you have a switch. The material that continuously comes into the disk has different isotopic properties because your sampling is coming from a different region of the giant molecular cloud that has been less contaminated in supernova product, and so it's a little bit different. And this material, again, falls predominantly close to the star and less further away. So the contamination of the new material dominates the inner part relative to the outer part. And so if you look at which fraction of the material in the disk comes from the initial material, the protosolar material, as a function of distance, you have that at time very early it's everywhere. After 50,000 years it becomes a function like the black one. After 100,000 years it becomes the one like the blue one, and so on. So you have more solid material closer to solar outer in the outer part in the disk, and more different from the sun in the inner part of the disk. And then the redistribution of material tends to smear this difference and make the outer disk less and less solar, less and less similar to the early material, and the inner disk more and more similar to the early material because dust starts to drift backwards towards the star. So if at some point you form the first planetesimal at two sides, like for instance the snow line and the silicate line, you sample the gradient. The disk has a gradient, you see, there's never dichotomy as long as you just have gas and dust. You sample this gradient at two locations, and then what you see later on is a dichotomy, because these guys have a ratio of early CI-like material and late infalling material that is different from these guys. So in this way, you can understand the dichotomy you see in iron meteorite parent bodies between non-carbonaceous and non-carbonaceous. But then, if you let the system evolve, the disk would homogenize and pretty quickly before chondrites can form. So clearly, as I said in the first lecture, at some point, a barrier has to form, and this barrier has to prevent outer material to go into the inner disk, so that this difference that is recorded in iron meteorite is frozen in the disk. In any case, what I was discussing in the first lecture is that we have two generations of planetesimals. We have those that form early, parent bodies of iron meteorites. We've seen, they can form at these two lines, snow line, silicate lines, but they are the chondrites, and the chondrites are planetesimals that form late. And the question is, how can they form late given the dust tends to fall onto the star? And so million years later, you should have only the early formed planetesimals and the gas, and all the dust should have been lost. This is a big open question in the community, And there are now a number of ideas. What we see when we look at extrasolar planetary disks in the million-year phase, the million-year age, what are called Titori disks, we see, again, the lights are not super, that these disks, this is HL tau, are fractured in rings. So there are at some point structures that develop in the disk where dust is trapped and cannot continue to drift towards the central star. So if the solar system developed such structure, then of course the dust would have been trapped in the rings, not disappear, falling into the sun, and then we keep this material in the ring, progressively reduce the gas because the gas is photoevaporated, and so the dust-to-gas ratio changes as you photoevaporate the gas, and then eventually you can form new generation of planetesimals once you have low enough gas in these rings. But we also observe debris disks. And debris disks are disks that contain dust and no gas. And the interpretation is that this dust is produced by collisions of already formed planetesimals that collide with each other, break, and generate dust. And so another possibility would be that the early planetesimals that form at this snow line and silicate line start to collide with each other, produce dust, and they start to do so when there is still some gas around. And this is what replenishes the disk of dust and allows the chondrites to form later. Which of the two is true boils down to the question on the origin of chondrules, because chondrules are a major constituent of these chondrites. These are particles that experience high temperature in the disk, and they all formed relatively late, at least 1.5 million years after the CAIs. And indeed, there are two gross scenarios for the origin of chondrules. One is that it says that these are just grains that survived in the disk, and at some point their temperature increased suddenly, probably because there were heating events in the gas, like shock waves or lightning is another possibility. And so these grains melted and recrystallized, and this forms chondrules. In this case, you need to preserve the chondrule precursors for millions of years, and the only possibility to do it is that the disk creates rings where dust is trapped and stays there forever. The other big camp of models for chondrule formation is that chondrules are products of planetesimal collisions. And in that case, of course, you regenerate dust as debris of the first generation. So the debate is not set, but I would say, and Paolo can confirm or deny, that in this Earth now, in the current times, the first scenario is the leading one, because of particular observations on the structure of the chondrules. I will not go in. So it seems that it's more dust that was preserved in the disk rather than collisional debris. So which would argue that the solar disk generated rings as we see in extrasolar disks. So although we don't understand the formation of these rings very well, it's a fact that they form. Okay, so one way or another, the disk forms planetesimals, early and late, and now we have to build the planets. To build the planets, there are two processes that have been widely studied in the literature. One is that planetesimals, once they are in the disk, can collide with each other. They are now 100 kilometers in size, so they have some gravity. So if they collide at low speed, they can stick by gravity. They come together. And so they form a bigger object. And then as the object is bigger, has more gravity, can attract more planetesimals and grow and grow and grow this way. So this is a planetesimal accretion. The other process is pebble accretion. So as a body is forming in a disk. The disk has planet gas, as planetesimal, as dust. Pebbles, just dust and pebbles for me are synonymous. And the planet can also accrete the dust that passes nearby and grow by accreting particle after particle. Each dust does not carry much weight, but if you accrete zillions of them, it's a way to grow. So this is a process that has been unveiled later than the first one, and there is a lot of literature studying this process. It's very interesting. So I will show here a few plots about each. So first, the traditional one, collisional growth. So here you have a few snapshots of a simulation conducted in the years 2000. So it starts, for instance, from a disk of 3,000 planetesimals. They are all the same in mass, 10 to the 23 grams. And they are initially, well, this is just a small sector of a disk around 1 AU, small eccentricity, small inclination, so they orbit and they collide with each other. When they collide, they stick and they grow. But when a planetesimal is lucky and has 3-4 collisions rapidly, so it starts to have more gravity, of course, it attracts more planetesimals, so it grows more, right? It's a capitalistic process in work. So you have money, you invest it, you gain money, and then you are more rich and you invest even more, and that's how Elon Musk is born. And this is the process that we see at the computer. And at some point, you see very rapidly there is one major guy that emerges and disperses the other planetesimals. The other planetesimals have grown as well. So here is the size distribution. So at the beginning, all planetesimals are the same, 10 to the 23 grams. After 50,000 years, it's this size distribution. After 100,000 is this one. After 200,000 is this one. So planetesimals also grow, right? But the big guys detaches from the size distribution. It's called an oligarch, so much more massive than the others. And its mass grows and grows. It runs away from the distribution of planetesimals. So this is a protoplanet, and if you keep doing the simulation, it keeps growing to becoming a planet. So this is the process of planetesimal accretion. It works in some extent, up to some limits. The limit is essentially set by a quantity that we call the Safronov number. Safronov number is given by this. So what's that? It's easy. So this is the first term is the escape speed from the liberation of the planet, from the surface of the planet. G is the gravitational constant. M is the mass of the planet. Rp is the radius of the planet. So this is the square of the escape velocity from the surface of the planet, 11.2 kilometers per second for the Earth. The second term is exactly the same, but it's reversed, and this is the mass of the star, M star, and this is the location of the planet from the star. So what is this? This is the square of the escape speed from the solar system at the distance where the planet is. And okay, why is this so important? Because when a planet is trying to accrete a planetesimal, first, typically, before having a head-on collision, it has just a near miss, so a close encounter, which changes the orbit of the planetesimal, giving to the planetesimal a change in velocity that is proportional to the escape speed from the surface of the growing planet. If this kick in the velocity is larger than the escape speed from the solar system, the planetesimal is ejected and will never come back. So will not be accreted, will be ejected. On the other hand, if this is less than the escape speed from the solar system, the planetesimal will be deflected on an elliptic orbit, but will not escape, so it will come back. And so the planet has another chance to accrete it. So accretion proceeds as long as the Safronov number is less than 1. And when the Safronov number becomes bigger than 1, the planet tends to eject everything rather than accreting it. Material is wasted. So planetesimal accretion is not indefinite, because as the planet grows, so M grows, and so the Safronov number grows, and so eventually the Safronov number turns from less than 1 to larger than 1, and accretion stops. To give you an idea, at 5 AU, the escape velocity from the Sun is 19 kilometers per second. And this is the escape velocity from a planet of 5 Earth masses. So if you have a planet growing, it can accrete planetesimals until it reaches 5 Earth masses, more or less, and then it starts to eject and stops growing. So it's difficult to form a giant planet. Of course, giant planet also has a lot of gas, but we need a big core of 10, 20 Earth masses in order to attract all that gas around Jupiter and Saturn. So it's very difficult to grow the core of a giant planet at 5 AU or 10 or beyond just by accreting planetesimals. and would take very long. You may say, but in reality, when this happens, there is still gas. So you say planetesimal is ejected, but the planetesimal is dragged by the gas drag, so it will not be ejected, it will stay in the system. Yes, that's true, but in that case, the planetesimal is circularized elsewhere. And what happens is this, so you have your protoplanets here growing in a disk of planetesimals. Here there are 5 protoplanets of 1 Earth mass each, okay? Then the planets tend to accrete and scatter, and there is gas. And because there is gas, there is no ejection, but the planetesimals that are scattered by the planets end up beyond the planets or inside the orbits of the planets, and the planets open a gap, and there are no more planetesimals to accrete. And so in this simulation, for instance, they grew to something like 2.3 to 2.8 Earth masses, and then they stopped. So planetesimal formation, planetesimal accretion is something that is naturally limited, can form planets as big as the Earth, smaller than the Earth, no problems. But if we are talking about the giant planet cores that are supposed to be at least 10 or 15 Earth masses, at large distances from the Sun, the Safronov number turns larger than 1 pretty quickly, and it's unlikely that the cores of the giant planets can form just by planetesimal accretion. This is the reason for which pebble accretion has been thought of. It's a great idea. The idea is that a protoplanet can also create dust particles. So a dust particle comes, this is the protoplanet, right, seen from the top. This is the radial distance, the Sun is down there, this is the azimuthal distance. The dust particle comes in like the gas along the streamline of the gas. But as it comes in, it feels the gravity of the gas as well. That's why the streamline is deformed, is bended. But in addition, it feels also the gas drag. And there's a combination of gravity and gas drag. The particle spirals and lands on the planet, delivering its mass to the planet. If the particle were not a particle, but were a piece of gas, it would follow instead this gas streamline. And if the particle felt only the gravity and no gas drag, it would just be deflected and not be accreted. So pebble accretion, really, by this combination of gas drag and gravity, can bring particles and onto the planet, and so deliver mass to the planet. It's another mode of growth of the planet. Pebble accretion is also its limits. It is proportional to the size of the dust to the power 3/2. And the reason is that the radius of the accretion cross-section that you see here in this figure is proportional to the square root of the particle dust size. This can be demonstrated. Of course, the accretion is in 3D, so the area of the accretion cross-section is the square of the radius, so it's proportional to the radius of the particles. But also the sedimentation of the particles close to the midplane is inversely proportional to the square root of the size of the particles. So the density of particles you have on the midplane available to be accreted by the planet is proportional to 1 over the square root of the size of the particle. So if you combine everything together, you get this. Now the pointer doesn't work. Yes, you get this dependence of 3/2. So what it means that for pebble accretion to be effective, you need that the size of the pebbles is rather large. And of course, you need that the density of your pebble layer is large. And so to have large particles, it's clear it's better to be beyond the ice line because ice is sticky and icy grains can grow more. To have a large density of particles, you need either a big radial flux of pebbles driven by gas drag, or you need that the dust is trapped in a ring and that this ring has a high density, and there the planet can accrete the dust in the ring, as shown in particular in this very nice paper that really studies the problem completely with hydrodynamical simulations. So, both processes exist. Both processes exist in nature. The question of which one dominates is an open question, and of course depends on the environment, right? Planetesimal accretion is very efficient close to the star. The Safronov number will never be larger than 1. because escape velocity from the sun is gigantic, but is inefficient farther away. Pebble accretion is efficient when pebbles are icy because they are big, and also it depends on the density of your rings or the circulation of dust. So a priori you don't know. It's great to have two processes forming planets, because the solar system has again another dichotomy, and this is a physical dichotomy. So as I said at the beginning, we have terrestrial planets which are rocky and small, giant planets which are gigantic, and the giant planets accreted the gas. And to accrete the gas, they had to form a core of at least 10, maybe more Earth masses to have enough gravity to trap the gas of the disk. And they had to form quickly before the gas goes away, in a few million years, like Mars. So say on the time scale of the disk, on the lifetime of the disk, the solar system somehow was able to make 10 Earth mass cores in the outer part, and in the inner part, Mars mass objects, because we've seen the Earth grows on much longer time scale of tens of millions of years. Mars formed in the disk, but it's only Mars mass. So Mars mass is 1/100th of the core of Jupiter. Okay. So there is a contrast of 2 orders of magnitude in mass in what the solar system has been able to form in the outer part versus the inner part. And the orbital periods are 10 times longer at Jupiter, and the orbital period is the clock at which everything happens. So this means that there is 1,000 contrast in between what the solar system does in the inner part and the outer part. How can you do that if you have the same process, right? There is no reason. I would expect a more smooth production and actually more production in the inner part than in the outer part. And I think so this switch in process can be the key. So the image that I have is that the disk, again, it's hot inside and cold outside. So you have only silicates and refractory material outside and icy pebbles outside. These icy pebbles are bigger. As we have seen, they are made of refractory particles entrained in an icy matrix. So they drift radially, they pass the snow line, they release, the ice evaporates, the little particles, millimeter-sized particles are released. And so this means that if you have, for instance, 2 candidate protoplanets, one just beyond the snow line and one within the snow line, the guy here sees a flux of pebbles that has twice the mass, because the mass of the ice disappears at the snow line, it becomes vapor. And in addition, bigger grains. And remember, pebble accretion is proportional to the size of the grains to the power of 3. The inner guy sees less mass passing in solids, half of the mass flux, and particles much smaller. And if you do a simulation of pebble accretion, you see that even if at the beginning you start with the same mass, the guy outside of the snow line grows to 20 Earth masses. In the time, the guy inside the snow line reaches more or less the mass of Mars. So a huge dichotomy mass due to this strong sensitivity on pebble accretion. And so this, I think, can explain why the big cores have been produced in the outer solar system, mostly by pebble accretion, the dominant process for the giant planet cores. But at most, pebble accretion produced Mars mass embryos in the inner part, and probably not even that. Another reason I will explain. And planetesimal accretion and mutual collisions between protoplanets form the terrestrial planets, as we will see. Here I stopped the simulation at 20 Earth masses for a reason. Because at 20 Earth masses, a planet starts to modify the density distribution of gas in the disk. This plot on the left is the outcome of an hydrodynamical simulation. The coordinates are the radial distance from the sun on the y-axis, so the sun is down here. This is the azimuthal coordinate. And this is a planet of 20 Earth masses. And the colors denote the density of gas. No dust here, only gas. So you see that the planet starts to open a shallow gap where the colors are blue, not so much gas, around the orbit of the planet. Has a spiral density wave in through the disk where the density is high. And the gas concentrates at the edges of the gap. because the density of gas has changed. In the beginning, it's a uniform or a power law, decreasing power law. Now has a gap and a pile up of gas at the border. The pressure gradient of the gas is modified, and this modifies the rotational speed of the gas. And this is what the plot on the right shows. This shows the orbital velocity of the gas normalized to the Keplerian velocity. Away from the y-axis is the same. So away from the planet gap, the gas is a little bit sub-Keplerian because of the pressure gradient, what I explained before. The gas rotates around the planet, the sun, more slowly than the Keplerian velocity, and we find what we know. But here, because you have this bump, this gap, this bump, as you can see, the radial velocity of the orbital velocity of the gas is strongly perturbed. And here, in correspondence of this pile-up, the orbital velocity of the gas can become super Keplerian, larger than Keplerian. And how much depends on the mass of the planet. At 20 Earth masses, just a little bit. At 30 more, at 50 even more, and so on. If the gas becomes super Keplerian, then the particles don't feel a headwind anymore. They feel a tailwind, so they are pushed, accelerated, and pushed out. So what does it mean? That if you have a particle far out, the particle feels a sub-Keplerian disk at this location, so it slows down, so its heliocentric distance decreases, but then it stops where the disk turns from sub-Keplerian to super-Keplerian, which is here in this 50 Earth mass example. So the dust drifts down and stops and cannot go further. So the planet, starting from 20 Earth masses, and even more when it's more massive, creates a barrier to dust drift. Dust can only drift to the outskirts of the planet orbit and no longer inside. What happens then? It happens what we can see in this artist view. We have a planet, and the dust is outside of the planet, tends to drift in, but cannot because of these barriers that accumulates there. There is no dust drifting in, so the inner disk becomes depleted with dust, is not fed anymore by the dust going from the outer disk into the inner disk. Maybe you have some residual dust close to the star, maybe regenerated by collisions of planetesimals, or maybe trapped in some other structure, but basically you get this transition. Is this a fantasy? Well, we do see this kind of transition disks around other stars. And in one case, PDS 70, we know this is due to a planet, PDS 70c, that plays the role of our growing giant planet, or PDS 70c is already Jupiter mass. And as you can see, the dust forms just a ring. Forms just a ring outside the orbit of the planet, cannot penetrate in the inner part, so you have a cavity of dust, and you only have the residual dust very close to the central star. So we think the solar system, as soon as Jupiter started to form and then Saturn started to form, they definitely passed over 20 Earth masses. The solar system acquired this structure. And this is very important to explain this separation of the disk in two distinct reservoirs. So the preservation of the dichotomy from the initial stage when the iron meteor and parent bodies formed forever, so allowing chondrites to form millions of years later from distinct reservoirs. So basically, the non-carbonaceous chondrites had to form in the inner part, close to the star, from the residual dust, not alimented by the outer dust, and the carbonaceous chondrites formed from the outer dust, where the icy, the first planetesimals at the snow line had formed. So this is the only way we conceive to maintain today, to maintain the isotropic dichotomy throughout the age of the solar system for millions of years. Okay, so we have formed the giant planets by pebble accretion. Great. There is one other process that is very relevant in planet, not really formation, but evolution. This is migration. A planet, when it forms, it perturbs the gas in the disk. I've already shown you the little gap, the spiral density wave. And because the distribution of gas in the disk is changed by the gravity of the planet and the azimuthal symmetry has been broken, then the gas can exert a gravitational force on the planet, and the planet in response changes its orbit. This is what we see here. So what do we see? Let me stop the movie fast enough. Okay, so here, this is an hydrodynamical simulation where we take, done by Frédéric Massé, by the way, where it's a piece of the disk, so the sun is at the center. The color shows the density of gas. Orange was the uniform initial density. Black means a lower density. White is an over density. And in this disk, a planet has been embedded with a given mass, a few Earth masses. And what you see, so first the movie is done in stroboscopic image. So the planet is not rotating around the star, but we take a frame every time the planet is aligned on this axis. Otherwise, get all hypnotized. So the planet by gravity generates the spiral density wave, white. This is an over density of gas. Of course, if there is more mass on gas here and here, this exerts a force on the planet. This force on the planet slows the planet down. And so the planet migrates towards the star. So we see in the movie it coming down. And actually here, as it comes down, it plots a plot of its distance over time. And you see that inward migration has already started. During the movie, the planet grows. And so you will see that at some point, the planet becomes big enough to open a gap around its orbit. Still migrates inwards, a little bit more slowly. You see a break in the migration speed, but still inward migration. So planets should migrate towards the central star. Faster if they are terrestrial super-Earth mass, and more slowly if they are giant and they start to open gaps in the disk, but they should all migrate. So now the question is, why are the giant planets so far out if they should have migrated inwards? Well, first answer, you could say, okay, they form even further out. They form 38 F30 AU, then they migrate, and by the time that this disappears, Jupiter arrives at 5 AU, problem solved. It's difficult to imagine that, you start to form core so far as 30 AU and stuff like that. It's not very believable. We've seen that the sweet spot to start to form objects is there's no line even in an initial disk. 5, 7 AU, so difficult to imagine that nothing forms there and all the giant planets form at 30 AU. I don't believe it, but some people do. Another possibility is that the giant planets grow really quickly, so they transited into this slower mode because they had open gaps, and the disk was at a very small viscosity, so this migration was really slow, and so they only migrated for a few AU. Maybe, but it requires many combinations. There is another possibility that in our solar system, we not only have Jupiter alone, we have multiple giant planets. Particularly, we have Jupiter and Saturn. And the coexistence of these two planets plays a role. It was already pointed out by Massé-Snellgrove in 2001. They did the first hydrodynamical simulation in the history with two planets. 2000, up to 2000, people were just doing one planet and the disk. 2001, first simulation with two planets in a disk. And they've seen something astonishing. So they put Jupiter at some distance, Saturn twice further out, and they looked at what happens. And they saw that Jupiter migrates towards the star, as it should. Saturn as well, it migrates faster because it's lighter. So it's easier to push for the gas. So Saturn approaches Jupiter until it's trapped in the 3-2 mean-motion resonance with Jupiter, where the orbital period of Saturn is 1.5 times the orbital period of Jupiter. And then see what happens. Even just before that, Jupiter stops migrating. Actually, its migration reverses a bit, and then Saturn blocks in resonance, and the planets don't move. And if you take a colder disk, so with a smaller aspect ratio, you can even transport the planets outwards. It also depends on the viscosity of the disk and so on. But certainly, so it's difficult to say exactly what was the migration pattern of the planet. But Saturn seems to be ideal to play to be instrumental to block Jupiter migration and retain migration quite far out. If this is true, then it's not needed to form Jupiter at 30U. It's probably not needed to form super fast. And I think this can explain the specificity of our system to have Jupiter so far out. And if you look at the distribution of extrasolar giant planets, the bulk of the giant planets are at 1-2 AU, not at 5 AU. 5 AU is already the tail of the biased distribution. I said before, giant planets must form by pebble accretion. It's the way to form their cores fast enough in a region where the Safronov number becomes bigger than 1 too quickly. But if you look in detail, this works certainly, without objections for the cores of Jupiter and Saturn. Uranus and Neptune are weird. Uranus and Neptune are weird because their spin axis is very inclined. Neptune has an inclination of the spin axis of 20-30 degrees, Uranus 98. And this suggests that these planets suffer gigantic collisions with protoplanets of a few Earth masses. You would say, well, Saturn as well has the same obliquity as Neptune, but Saturn has an explanation, dynamical explanation, due to a spin-orbit resonance. It's something complicated, but it's true. We don't need collisions to tilt Saturn. It's understood. But Uranus and Neptune, there is no other dynamical explanation than collisions. So if these planets are formed entirely by pebble accretion, then there are no giant collisions, so the spin axis should be perfectly vertical. So the model we have developed a while ago with Andrei Isidoro, 10 years ago now, to form Uranus and Neptune is the following. So in the disk of gas, which is represented by this trapezium, color trapezium, beyond the snow line, so the big cores start to form. Jupiter and Saturn accrete their envelopes because they form fast enough. And as we have seen, they block their migration. So they don't migrate anymore, or they move a little bit outside, but it doesn't matter. Beyond them, you have some other cores that are forming a number, maybe, of masses of the order of a few Earth masses. The colors denote the mass. What would happen in that case? Would happen that Jupiter and Saturn don't migrate because of the interaction I showed before. The other ones want to migrate toward the Sun, but they see Jupiter and Saturn inside of their orbit, and it's difficult to cross Jupiter and Saturn. They tend to be captured in resonance with Jupiter and Saturn. And so by being captured always in the same resonance, these protoplanets collide with each other and grow. And so here, for instance, you have a moment when we have 4, 2 are about 10 Earth masses, and 2 which are still pristine. If you wait a little bit, then we become 2, of course. And so this produces, at the end, 2 planets of comparable masses and of 15 Earth masses. Here we go. And of course, because these planets form by merging, their spin axis should be random. So in this case, for Uranus and Neptune, it's a combination. Pebble accretion producing intermediate mass planets of maybe 3, 5, 7 Earth masses, I don't know. And then these planets try to migrate, but are blocked by Jupiter and Saturn, so they have necessarily to merge. And so the final Uranus and Neptune are produced by giant impacts, and this can explain their obliquity. In this game, it's great because everything happens in the outer solar system thanks to the fact that Jupiter and Saturn have blocked their migration. The inner system is totally unaffected. So the terrestrial planets can do their own stuff and slowly keep growing by other processes and form so a second set of planets. And this division between the outer solar system and the inner solar system continues beyond the accretion of the first planet. Yeah, what about the terrestrial planets? So, terrestrial planets, again, because they exist, so understand how they form. So because pebble accretion has been the dominant process of the cores of the giant planets, the most natural question is, could they form by pebble accretion? So huge controversy. This. We think, and we published a full paper on it, that this is really unlikely, and for a number of reasons. First, we have seen, it's in the data, the Earth forms on a time scale much longer than the disk lifetime. And pebble accretion works only as long as there is gas, because you need the combination of gravity and gas drag. Second reason is that if the Earth had formed big during the gas disk lifetime, it would have started to migrate. And migration for small planets like these is proportional to the planet mass. So Earth and Venus should have migrated towards the sun. Mercury, not much, but it could have been pushed in a resonance by Venus, but Mars should have been left behind. Or the planet in terrestrial planets are very nicely, regularly spaced. There is really no sign of migration, which suggests, again, that the planets grew slowly, and by the time the gas disappeared, the masses of the planets were of the order of the mass of Mars, and Earth and Venus took much longer to form by further collisions. And finally, we have seen that there is this Jupiter barrier, because the solar system is divided into an inner disk which has non-carbonaceous isotopic properties, an outer disk that has different isotopic properties. So there was no feeding of the inner disk from material coming from the outer disk. So the amount of mass available in the inner disk was necessarily limited. There is not this continuous flux of dust that feeds pebble accretion to be really efficient. Maybe, and this cannot be excluded, the embryos like Mars, protoplanets on the mass of Mars could have formed by accreting local dust with non-carbonaceous isotopic properties if this dust was trapped in a ring. This cannot be excluded. But this is not the Earth. It's protoplanets, maybe of the mass of Mars at most. So, for the formation of the terrestrial planets, I think the classic model, which is that based on planetesimal collision, works much better. We are in the inner system, so the Safronov number is always less than 1, because the escape velocity from the Sun at the Earth distance is 45 kilometers per second, and the escape velocity even from the Earth is only 11. So the Safronov number is always very low. You only have accretion, you never have ejection. So the idea is that from a disk of planetesimals, you have planetary embryos that form, like in the sequence we have seen before. So this is a simulation. You start from a disk of planetesimals. You have the radius of the planetesimals as a function of distance. And from this disk, you have the oligarchs, the embryos, that start to form. And slowly over time, this oligarch population stretches out. The masses of these oligarchs naturally reach the mass of Mars over time in about 1 million years. So you rapidly go to a system that has a combination of planetesimals and planetary protoplanets, planetary embryos, which are represented, the planetesimals in green, the protoplanets in red. Jupiter has already formed because it forms within the lifetime of the disk. When the disk disappears, the system continues to evolve under mutual perturbations from Jupiter. All the protoplanets leave the asteroid belt. The others inward of the asteroid belt tend to collide because the Safronov number is too low. So by colliding, they grow. And this forms, as we will see, on a time scale of about 50 million years, a system of 3 planets rather than 4. So these 3 terrestrial planets, some simulations for 4 or 5. I mean, there is some random, but this would be the terrestrial planets formed around 1 AU, not in the asteroid belt, on time scales of tens of millions of years. So this is the model conceived, first of all, by George Wetherill at the time when simulations were really primordial, and then simulated by a number of people. It works really well in a number of aspects. So a few terrestrial planets are formed in the terrestrial planet zone, not in the asteroid belt. Typically, if you put enough the good mass at the beginning, you get the planets that are Earth mass. The orbits are quite good in terms of orbital eccentricity and inclinations. The time scale are correct for the Earth, typically tens of millions of years, of the order of 50 million years. There are these impacts among embryos, so giant impacts, and we know the Earth at least suffered one, which is the one that formed the Moon. So this is not an oddity, because the planets do form first by planetesimals forming embryos, then embryos colliding with each other. to form the planets. And also there is some way to deliver some icy rich bodies from the giant planet region to the Earth. This Paolo will talk about this stuff. But there is a problem, and the problem is that in the kind of simulations I just showed the animation of, the planet that is formed at the location of Mars is typically too big. So in this plot, I don't know, a link came out. In this plot, okay, keep it with the label. So the squares show the real masses of the planets: Mercury, Earth, Venus, and Mars, mass versus heliocentric distance. And the dots show the planets produced in simulations. So you see, for Earth and Venus is pretty good. There is even a tendency to form a small planet like Mercury inside. But for Mars, typically you get planets as big as the Earth or Venus, which is not the case. And this number of things have been tried, nothing seems to work, except postulating that the planetesimal and planetary embryo population, instead of being extended up to basically the orbit of Jupiter, was confined in a narrow ring, more or less from 0.7 to 1 AU or something like that. And if you do that, it has been shown already in 2009 that the planets that are produced in the simulations, which are here represented by these open dots, reproduce the pattern of the real terrestrial planets, with big terrestrial planets at the center and the smaller terrestrial planets, Mercury and Mars, on the wings. And so the question is why there is this confinement of material there. But I showed you that the early planetesimals tend to form at snow lines, or silicate line, or the snow lines, condensation lines, sorry. So like the silicate line or the snow line. So in some sense, it's natural that the first planetesimals are concentrated in a narrow region. And this may be what we see then reflected in the mass distribution of the terrestrial planets. Before understanding that, how planetesimals form and the link of planetesimals with condensation lines, we thought the planetesimal had to be a very rare, and then quite innovative scenarios have been produced, invoking the migration of Jupiter, early instability, and so on. But I think this has no reason to be invoked anymore. Last event of the solar system, the giant planet instability. Because planets, when they form, giant planets forming the disk of gas, they definitely migrate. And we've seen the animation forming Uranus and Neptune. So at the end, the planets are all in resonance with each other, because migration brings planets in resonance with each other. Until planets enter in resonance with each other, their configuration changes, and only when they go in resonance with each other, the system stabilizes in a stable relative configuration. But what comes out then is something like this, where the giant planets are very close to each other. This comes out of the simulation I showed you before. Jupiter and Saturn are in 3-2 resonance. Uranus and Neptune are in other resonance with Saturn. You can do different simulations. Maybe you can have different resonances. Depends also on the viscosity of the disk, but always a resonant chain, relatively compact. And this is not where the planets are today, right? Because today the planets are on a more separate orbit, spanning from 5 AU to 30 AU, and there are no resonance relationships. So how can we reconcile the two? And the way to reconcile the two is via a giant planet. It is a phase of dynamical instability of the giant planets that occurs after the gas is removed. Because as long as the gas is there, it keeps the planets in resonance. They cannot move. But once the gas is removed, the planets in principle can evolve dynamically. So the model that we have elaborated already 20 years ago, but then modified, and the current model dates from 2012, 2017, is that so the giant planets were in resonance, as in the simulation that produces them. They were surrounded by a disk of planetesimals, the ancestor of the Kuiper belt, which was relatively massive, contained 10, 20 Earth masses or something like that. When the gas disappeared, so the gas stopped keeping the planets in resonance, the planets were interacted gravitationally with the trans-Neptunian disk, dispersed in the trans-Neptunian disk, and the orbits of the planet being modified in return. And modify one day after another. After a while, the planets can break the resonance chain and become unstable. In this animation, it happens relatively late, so I have some time to discuss, but probably happened in the first 100 million years. And then when the planets become unstable, they scatter off each other, they separate violently from each other, they disperse the trans-Neptunian disk, and they land on orbits very similar to those they have now. Here you see Neptune reached 30U, circular orbit, Uranus 20U, circular orbit, Jupiter and Saturn 5 and 9AU, with some eccentricity, corresponds really pretty well to what we observe. And so the instability would be the link between the primordial orbits that come out of the disk of gas and the current orbits that we see now. It's interesting that in this phase of chaos, of course, a lot of things can happen. And the simulations that are nice, that reproduce the solar system that I just showed, are about only 5-10% of the overall simulations, and are the simulations in which, during the phase of instability, Jupiter and Saturn encounter Uranus and Neptune, but don't encounter each other. And this is the requirement. Jupiter and Saturn do not have to encounter each other if we want Jupiter to remain on an orbit with moderate eccentricity. But in many simulations, they do. They encounter each other. And then it's a total disaster. The solar system explodes. Many planets are ejected, sometimes Saturn as well. And Jupiter is left on a very eccentric orbit of about 0.4. So that's totally crazy for the solar system. But if you look at extrasolar giant planets, in particular those the furthest from the sun, say 1 to 5 AU, these are the red dots. The size of the dot is related to the mass. And this is a major axis eccentricity. You see that this eccentricity is typical of what we see around other stars. And indeed, it's suspected, and Sean Raymond, that you will see later in the week, he is not speaking, developed a model showing that the overall eccentricity distribution of extrasolar giant planets can be explained if 90% of the giant planet system become unstable. And so our own system as giant planets has become unstable, and we owe the low eccentricity of Jupiter to the lucky event that Jupiter and Saturn avoided mutual encounters. Otherwise, we would have a very eccentric Jupiter as well. So is there a trace that everything of this happened while the giant planet orbits can be one? We have done a lot of studies to show that the entire shape of the outer solar system can be reproduced in this instability. I will go really quickly because otherwise it becomes too long. But for instance, for the Kuiper belt, the idea is that the cold population is the local population that was there, 45 AU, but the hot population is the population scattered, dispersed by the planets during the instability that can be trapped in the same region of the cold belt, but preserving the inclination. So this is the inclination distribution in the model, in the data, they match. The eccentricity distribution, they match. And of course, because these objects in the hot population are implanted from the closer in, then of course they can have different properties from the cold population, which is local. And this is what we see. We have also the production of the scatter disk and the Oort cloud. And so in terms of the Kuiper belt, this reproduces all the features of the Kuiper belt, scatter disk and Oort cloud very well. For the irregular satellites, can explain them as well, because the giant planets have a phase of close encounters with each other. And when they encounter with each other, they are already unstable. So there are already many trans-Neptunian planetesimals flying through the system and through the terrestrial planets. So when two planets encounter with each other, they can do so in a sea of dispersed planetesimals. And so what can happen is, for instance, when Uranus and Neptune encounter with each other, at some point their hemisphere, their sphere of influence overlap. And some planetesimals can be at the same time in both sphere of influence. And this is a way to modify their orbit and trap them around the planets. So this is a cartoon, but this is the results of the simulations. And the red triangle show the orbits of the regular satellites of the 4 giant planets in terms of semi-major axis, eccentricity, and inclination. This is for Saturn, this is for Jupiter, Uranus, and Neptune. And the dots are what is trapped in the simulation. So we really trap the satellites on the orbits on which they are observed. For the Trojans, it's something similar. During the dispersal of the trans-Neptunian disk, the planetesimals go around in the giant planet region, like centaurs, but cannot enter the stable regions. So the planetesimals that are dispersed are these blue dots, but the regions around L4 and L5 of Jupiter are stable. So these planetesimals cannot enter into these regions. But Jupiter has an encounter as well, say with Uranus. And that kicks the orbit of Jupiter inwards. And the region of the stability of the Trojans kicks inwards as well, because they have centered on the orbit of the planet. And so some planetesimals, which were outside of this region, can be now inside of these regions. These are the green ones. And then they are trapped forever. And again, the simulations reproduce extremely well the orbital distribution of the Trojans. Here, the Trojans are characterized by, but not the semi-major axis because it's all there, but the amplitude of libration around the equilibrium point of Lagrange, so which is this angle, the eccentricity and the inclination. The little dots are the real Trojans, and the 3 open symbols are the orbits of the Trojans captured in 3 different simulations showing this game. So it works very well. And of course, trapping Trojans from planetesimals dispersed from the disk, the same disk that goes into the hot population, explains why the size distribution of the Trojans and the size distribution of the hot Kuiper belt are the same and different from that of the cold population or that of the asteroids. What about the asteroid belt? Because with this dichotomy business, we would like to say that carbonaceous planetesimals formed beyond Jupiter. We need the Jupiter barrier to keep the dust beyond Jupiter, so they should form beyond Jupiter, but they are in the asteroid belt today, which is between Mars and Jupiter. So how do they go there? There are various dynamical mechanisms, but I think the reference one is this one studied by Sean Raymond and Andrei Isidoro. So the planetesimals in the giant planet region are scattered as the giant planets grow. So here you see Proto-Jupiter, Proto-Saturn, and they grow, they become bigger. As they become bigger, they disperse the planetesimals. Some are sent out, some are sent in. And those which are sent in by gas drag are partially recircularized and they land in the asteroid belt. And so this is how planetesimals that form beyond Jupiter, beyond the Jupiter barrier, can be found in the asteroid belt today. The terrestrial planets do the same thing, right? They form, they collide with each other, there were local planetesimals, they scatter these planetesimals. Some planetesimals can be trapped in the asteroid belt, particularly if the instability of the giant planets occurs after a few tens of millions of years. So this plot shows initially all planetesimals are in the ring at 1 AU, the asteroid belt is empty. And this shows the final distribution of the the distribution of the planetesimals after the instability, and the red ones are those trapped in the asteroid belt. So some planetesimals some asteroids in the asteroid belt can also be captured from the terrestrial region, and some can be endogenous. So now the debate is what is endogenous, what comes from closer in, what comes from further out. So carbonaceous asteroids probably come from beyond Jupiter. Among the non-carbonaceous asteroids, it's possible that some are endogenous, others come from the terrestrial planet region, maybe dense tichondrites, more similar to the Earth in terms of isotope. We don't really know. And then there is the giant planet instability, and the giant planet instability reshuffles all the orbits. So even if before the giant planet instability all orbits had been coplanar and circular, after the giant planet instability, all the orbits are all dispersed by the instability. Some asteroids become so eccentric that they will be unstable and will be removed. And what remains in the stable region reproduces very well what we see. Here in this simulation. By the the blue dots are the simulated asteroids. The red dots are the observed asteroids. I think we reproduce the orbital distribution. So I started saying, oh, the asteroids are excited in eccentricity inclination, something should have excited them, and so on. The giant planet instability is certainly can do it. And in addition, the implantation can also implant objects on non-circular and non-inclined and inclined objects. So we conclude here, but instead of doing the summary of what I explained over 3 hours, I would like to wrap up and talk about astrobiology a little bit, because at the end this is an astrobiology conference, so we sort of invited here is to set up the stage. So what are the key ingredients, the key aspects that made the solar system as it is, and what were their implications in terms of astrobiology and habitability? So it's my view. First thing is that the innermost planet beyond the snow line grew very big and became a giant planet like Jupiter. This was important. Why? So first, created the Jupiter barrier, and this divided the disk in two, which is the non-carbonaceous, the carbonaceous thing. So you would say, who cares? I mean, the habitability on Earth certainly does not depend on the ratio between titanium-50 and titanium-47. But the important thing is that the Jupiter barrier blocks the flow of dust from the outer disk to the inner disk. And this is important because it means that the planets that can form in the inner disk can do so only from the local material. This local material is not continuously fed from something that comes from further out. So the terrestrial planets formed from a limited amount of material available and had no more. And this is why the terrestrial planets, are not very big and formed slowly, as we said, in the lifetime of the disk of order of mass of Mars, and takes longer to form something major like the Earth and Mars and Venus. And this is in turn important for habitability for two reasons. Because if you form a planet very quickly, it captures a primitive atmosphere of hydrogen and helium from the disk. And then you have an atmosphere dominated by hydrogen and helium, and not an atmosphere dominated by gases outgassed from the inside out. So these kind of planets are observed, and most of super Earths we observe around the other stars have these envelopes of hydrogen and helium. But think about it. For instance, if you have an atmosphere of hydrogen, you cannot produce oxygen, right? Even if you have bacteria that produce oxygen by some photosynthetic process, this oxygen would combine with the hydrogen and create water. So it will never oxide your atmosphere. So Earth would be radically different. And another aspect is that because the planets remain small, they did not migrate very much. You need massive planets to perturb the gas and be perturbed in turn to migrate. If the Earth had formed within the lifetime of the disk, because the continuous flow of mass from the outer disk, Earth would have started to migrate. And even if it started to form in the habitable zone, would have left the habitable zone and go closer to the sun. So really, we owe the basic properties of our terrestrial planets, lack of primitive atmospheres, small masses, no migration, and so on, to this barrier of Jupiter. So it's much more profound than protecting us from titanium-50 versus titanium-47. The second big event that shaped the solar system was the formation of Saturn. Saturn presumably followed the formation of Jupiter, giving lags behind in terms of mass, and is instrumental to block Jupiter migration. I think this is sure. Everybody finds it in their own simulation. If you put Jupiter and Saturn, they go in resonance and they stop migrating. This is important to keep Jupiter far out rather than migrate down. When you look at the extrasolar giant planet distributions, most giant planets are at 1 to AU. And if the Jupiter had come to 1 to AU, well, it would have disturbed the formation of terrestrial planets, and I don't know what would have happened. But if Jupiter is retained at 5 AU, as I showed, Uranus and Neptune formed by collision and tilted, but who cares? In terms of habitability, it's not important. But the terrestrial planet region remains undisturbed. Everything happens far away. And so this little mass that we have is not wasted and so on. Uranus and Jupiter and Saturn, in addition, not only did not migrate, Jupiter did not migrate in the terrestrial planet zone, but Jupiter and Saturn together retained Uranus and Neptune or their precursors in the outer disk. They not let them migrate through the disk towards the Sun. And if they've done so, so in absence of Jupiter and Saturn, we would say the Uranus and Neptune or their precursor would have migrated through the entire disk to the inner edge of the disk, crossing the terrestrial planet region. And that would have, of course, destroyed, captured, swept away, dispersed most of the mass. So who knows what would have formed in the terrestrial planet region if that had been the case. The last aspect is that at the instability time, so the giant planet became unstable. We see that recorded in their orbits and in the structure of the outer solar system. But when this happened, the two major planets did not have close mutual encounters. Jupiter and Saturn did not see each other. And this is what allows them to remain, and Jupiter in particular, on an orbit which is very eccentric, but very mildly eccentric, 0.5%. No, 0.05, yeah. So 5% of the eccentricity, which is really little. If Jupiter and Saturn had close encounters with each other, as I showed, Jupiter would have been much more eccentric. And as soon as the biggest planet of the system is eccentric, all the other planets become eccentric. It's a law of Newton. Secular eccentricity distributes between planets. So it's not possible to have a circular Earth with an eccentric Jupiter. And then if the orbit of the Earth becomes eccentric, it means that the distance from the Sun is not constant. And so you pass once per year very close to the Sun, and one per year very far from the Sun. So the irradiation of the Sun becomes very variable over the year. So this creates an exceptional change in climate, right, on the year. Our season, nothing compared to that. So I think probably planets on eccentric orbits are not habitable. And we owe the fact that we are on a almost circular orbit, the fact that Jupiter kept its almost circular orbit. So these are little grains for thoughts when we talk about habitability in solar system in general, that maybe, of course, there can be many exotic planets or life can find different solutions, very different to ours. But when it comes to the habitability of our solar system, or our Earth in our solar system, I think that these three basic contingencies are really necessary to make the solar system as it is. Thank you.